Welcome to The Click. This is Roots Rules Part 1. Starting with the first rule, root exponent relationship. The nth rule of a is equal to x. If and only if x is raised to the power of n is equal to a, which is the second part of the formula. Did you get it? We say that exponents and rules are completely the inverse operations for each other. So if we have the nth rule of a number, which is a, and that is equal to x, we can say that x to the power of n, which is our root and it becomes our power, is equal to a. Only that. If that's not true for the case, then the relationship or the operation is completely false. Let's have an example. The second root of 25, which is equal to 5. I even don't have to write the 2 on the root, 25, because when a root symbol doesn't have any degree, we know that it's 2. This is equal to 5. So we know that when 5 is raised to the power of the degree, so 5 to the power of 2, it should be equal to our radicand, or our number inside the root, which is true for this case. And that is why we say that it's correct. Another example. For example, I have the third root of 8, which is equal to 2, right? So 2 to the power of 3 is equal to 8, and only that makes the root exponent relationship correct. This was the first one. Off to the second one, root of a power rule. The nth root of x to the power of m, okay, this is x to the power of m, we are missing a sign in here, is equal to x raised to the power of m divided by n. What does this mean? We mean that when we have a root, okay, and the radicand of us has a power, at that time, that root completely, the operation is equal to the radicand to the power of m divided by n. N stands for the degree of the root, and m stands for the power of the radicand. So here we have the formula. The nth root of x to the power of m is equal to x to the power of m divided by n. So, for example, I have the third root of 8. This is the same as a to the power of 8, which is 1, divided by 3. Okay, so this is the whole operation. If I had to simplify it, I would say 2 to the power of 3, which is 8, right? To the power of 1 divided by 3, which will be 2 to the power of 3 divided by 3, which will be 1. So our answer is 2. And this is correct because when we go to the first part of the operation, it's the third root of 8, and third root of 8 is equal to 2. Another example, x plus y to the power of 8. And this is their 12th root, okay? So 12th root of x plus y to the power of 8 is exactly equal to x plus y to the power of 8 divided by 12. And this can also be written as x plus y to the power of 2 divided by 3, if we simplify this fraction. And yeah, this is the second rule. The third rule, root and power cancellation rule. The nth root of a to the power of n is equal to a. It's very, very simple because, the root and the power will cancel each other if they're the same number. And that is why, the operation will equal a. So for example, I have the third root of x to the power of 3, which is equal to x. For example, the 12th root of x plus y to the power of 12. This is exactly x plus y, and nothing has changed. For example, I have the third root of minus 5 to the power of 3, this will be minus 5. Okay? Going for the fourth rule, root and power cancellation rule, but this time we have an even index case or even degree case, okay? If the degree of the root n is even, then the nth root of a to the power of n is equal to the absolute value of a. Okay, so I have a number. For example, the second root of x to the power of 2. This is equal to the absolute value of x. You know what absolute value means, right? When the number or the variable doesn't have any symbols, neither plus nor negative. And why is this correct? Because the absolute value is needed, because an even power removes the sign of the original number. Okay, so when we have an even power, it removes the sign or the symbol. So at that time, we know that, we have an absolute value with no signs. And therefore, this is correct. Let's do another example. I have the fourth root of the number minus 3 to the power of 4. Okay, please pay attention that the power also needs to be, equal to our root or our degree of the root. So when my degree is an even number and it is equal to the power of my radicand, I know that the number should be an absolute value. And the result is our number itself, but in absolute value. This was the fourth rule. Let's go for the fifth one. Negative radicand rule. If the radicand is negative, this number, and the index of the root is even, the root represents an imaginary number. I represent imaginary number, okay? Why is this correct? Because let's say that I have 2 times 2, which is equal to 4, plus 4, right? But I also have minus 2 times minus 2, which is equal to 4, because minus times minus is equal to positive, or is equal to plus, right? That is why the sign of the 4 doesn't change. This is why that there is no any real number that can be multiplied by itself and give a negative number, because both the positive signs and the negative signs, when they are multiplied by each other, then the sign of the result will be positive. And that is why, our radicand is basically, the result of a number being multiplied by itself a few times. And when the radicand is negative, we know that there is no any number that can be multiplied by itself and give a number that has a negative sign. So that is why people could not solve this, so they invented imaginary number. And we actually studied this on the first lesson, Introduction to Arithmetic. I hope you remember that. So that is why we have, for example, the second root of minus 4, for example. The answer to this will be 2i. Because 4 itself, when it has the root of 2, so 2 times 2 equals 4. So the second root of 4 is equal to 2. But because my 4 is a negative, that is why this is an imaginary number. So I need to put an I next to 2 as well. So it becomes 2i. So please remember that whenever you see a negative radicand, at that time, do the operation, but only add an I at the end of the result. We are done, everyone. I hope you enjoyed this lesson and see you in the next one. Sources page.